Okay, so we're live. I'll see about...
I see you're speaking, Professor, but you are
ah,
muted.
very good. Thank you. So we are live. I just, I've got a bit of, I don't know, I think it's the fact that it's warmer and I'm starting to get spring allergies that I'm coughing a lot, so I didn't want to cough in all of your ears this morning, so I had it on mute more than I do, and I forgot to take it off. Thank you for telling me. Okay, so we are live on YouTube. I'm just trying to figure out how to get the link. Let me get that now while we... I used to be able to tap on the Streamlabs link and it would take me there, but it's not doing it this morning, so let's just do that and put that into the materials 236 link. Okay, so I want to well, let's have a look, see what we're doing. I do want to go back over Thevenin and Norton, but mainly so that we can tackle. Actually, I want to go over superposition as well, but mainly so we can tackle the tutorial, because I'd like to do that first up. Next week there is a break. We have the Good Friday break. So, well, I suppose it's Easter break. It will be Saturday, won't it? So I don't think there's any classes next weekend. And what I would like to do when we get back is start the capacitance, inductance, reactance, impedance pieces. And there's no really new material in that. The only thing that changes is we do exactly everything we've been doing so far, except we do it all again with complex numbers, right? And there's a little bit of a intricacy in getting the right complex numbers. But it's mesh analysis, nodal analysis, superposition, Thevenin, Norton, series, parallel, Ohm's law. Instead of Ohm's law being V equals IR, we now change that slightly to V equals IZ, where now Z is an impedance and possibly a complex valued impedance. So it has a real component and an imaginary component. But we'll do that in about 2 weeks' time. Okay? So that's where we are. I don't think I'm going to be talking about anything too new today, but we'll have a look. So as far as the assessment, we have the usual thing, a homework and a lab due today, the superposition lab. I thought I might. Let me just go to the real live version so we can check on that. That's the wrong course. Might have to log in again. No, wrong one. So what I might do is I might move right, I had a lot of stuff due next week and I'd forgotten that that week was Easter weekend and that we were having a break. So what I might do is let me do that now. I might move all of those so that they're due a little later. I might have to actually get in there and I might actually have to get in there and make them available later than that, but that way you've got quite a bit of time. I would like to keep the superposition lab due today. I moved the Thevenin. I remember now. I forgot to update my slide. It just has a screenshot of this page. I moved the Thevenin and Norton assignment to be due after we did the tutorial, and I was planning on doing the tutorial in that today. So we'll do that today, and it doesn't seem very fair to have you do the tutorial and then immediately have a homework assignment in it due. At least this way you get a bit of a chance to do the tutorial and have that sink in before I ask you to do the homework. Okay. So yes, this page is out of date. So the only thing that is due here is that lab, and those three things, that one and those two, are moved to what it'll be. It'll be the 10th. Okay. That's where we are with the midterm. So far I've been pretty happy with the way, I think 7 people have taken the midterm so far, and I've been pretty happy with the way everybody's been going. So if you haven't booked yet, please book a slot and try and get it done before the Easter break. If you can't, that's okay. I think there's some slots available after Easter, but after Easter I'm going to be releasing slots for the second midterm, so which is about mesh analysis and nodal analysis. So please get the first midterm done as soon as you can. So I sort of talked about maximum power transfer and Thevenin and Norton already, but what I really want to get done today is that tutorial. So, but I thought before we did that tutorial, maybe I should have reorganized this. I did want to talk about Thevenin and Norton first, but what I'll do is I'll just have a look at the questions on the tutorial first, and then maybe talk a little bit about how to approach each of them, and then we'll do the usual thing about splitting up into breakout rooms and tackling one of the problems in each breakout room. Okay? Any questions so far? Okay. So let's have a quick look at the tutorial. I released that a while ago, but we haven't actually had a chance to do it. So let's have a look. So here's the first superposition question. And remember, because I'm asking you to do it using superposition, I'd like you to use superposition. So that means because this particular circuit has, in fact, let me just grab a screenshot of that and put it in over here. In fact, let's do this. Let's just move it over like that. Okay, so what superposition says is that we first of all select each independent supply in turn. So here we've got two independent supplies. We have a IS on the left, and just to the right of middle we have VS. Right, so those are the two independent supplies. So we select one of them. Let's select IS first, and we replace all the other sources with their ideal sources. And remember, an ideal source is one that sets the value of the source to 0. So here we set the value of the source VS to 0, which makes it just a wire, right? Because if the voltage drop across VS is 0, then the node on the top of VS is at the same voltage as the node at the bottom of VS, so it's the same node. And then we solve for the desired value. In this case, the desired value is IX, the current flowing through VS. And then we do the same thing again for the other way around. With we replace IS with its ideal, which is just going to be an open circuit, because if 0 current is flowing through that branch of the circuit, then it's as if there was an open circuit there. And then we again solve for IX, and then once we've got those two values for IX, with only the effect of one of the independent supplies on it, then we add those two values of IX, and that will be the solution for the whole circuit. And I think the second question is pretty similar, right? And let me just, in case you don't have access to OneNote, I'll just pop the tutorial into the materials channel, so that should be there now. Okay, any questions about the superposition piece? Okay, so remember Thevenin, there are the idea here. Let me go grab a screenshot of the Thevenin pictures. Right, so there's Thevenin and there's Norton. Okay, so the idea here is that we can replace everything in the circuit on the left with, in the case of Thevenin's theorem, a single voltage source, VTH, and a single series resistor, RTH. Similarly, with Norton's theorem, we can replace the whole circuit on the left with a single current source and a parallel resistor. And the neat thing about that is that the Norton resistance is equal to the Thevenin resistance. So Rn equals RTH. Now the problem with this is there's three techniques that I gave you to analyze this circuit, or to find RTH. And the first one, the equivalent resistance approach, requires that there be no dependent sources. And the trouble with this circuit is that there is a dependent source, right? The diamond with the 2400 IX above it is a dependent source. It's a voltage source, but it depends on the current IX. So we can't use the equivalent resistance approach. So that leaves either the open circuit voltage short circuit current approach or the applier voltage approach. And either of those will work. The issue though is both of them only give you the Thevenin resistance. You also need to find either the Norton current or the Thevenin voltage in order to solve the problem, right? Because remember, the Thevenin equivalent is both a voltage and a resistor, and the Norton equivalent is both a current source and a resistance. Okay, and then the other question is pretty similar. It's just we've got a current source on the left instead of a voltage source. So remember the the open circuit voltage short circuit current approach. We act the open circuit voltage. To find the open circuit voltage, we pretend we have a voltmeter, right, with probes that we connect across here. And that's whatever voltage is currently being exhibited across the outputs A and B is the open circuit voltage. Because it's open circuit, there's nothing flowing through this resistor. There's no current flowing through this resistor. So that voltage is the same as the voltage here. Right? And then the other piece is the short circuit current approach, or the short circuit current, and there you need to pretend you've connected an ammeter here, and you want to know what that current is. Okay, so it's the short circuit current. And with the open circuit voltage and the short circuit current, you divide the voltage by the current. That will give you the Thevenin resistance and the Norton resistance. And the open circuit voltage will be the Thevenin voltage, and the short circuit current will be the Norton current, the current of the Norton source. Any questions about either of those? Okay, so what I'm going to do is I'm going to split. Let's just have a quick look. Yeah, I think that one's pretty similar. It's just swapping the voltage source for a current source. So what I'm going to do is I'm going to kick off the breakout rooms. There are going to be four breakout rooms, and we'll do all four questions in parallel, right? So the top room will do question 1, the second top will do question 2, third top will do question 3, and the last group will do question 4. Okay, so let me just see if I can do that. Breakout 4. For some reason it's decided to not give everything. Let's just see if there's any. Ooh. No, that was a while ago though. Okay, let me I think it's call back. Let me try calling everybody back. I'm sorry about that, but for some reason not everybody went to the breakout rooms. So I'm going to try that again. Otherwise, I might, if you're left in the main room after the breakout rooms get created, please migrate to one of the rooms, and I might get, to make sure it's a bit even, I might get people to move once they've allocated themselves. But try and choose a room if you need to that's got fewer people in it. Yep, so Alex, if you would, yeah, go for it. Thank you. Okay. Okay, so this room is going to be doing question 4. Everybody okay with that? Yeah? I take it you can hear me?
Yep.
Yep.
Yeah, we hear you.
Okay, good.
Yeah, we can hear you.
Okay, I'll let you start at it. I'll probably give you about 10 minutes to try and get it done, okay? Okay, so this room is trying to tackle question 3, okay? And I'm going to give everybody about 10 minutes, so it'll be about 9:35, and I'll call everybody back. Okay, so this room is tackling question 2, and I'll give everybody about 10 minutes to have a go at it. Anybody got any questions yet? No? Okay. Hi, this room is tackling question 1. So please have a go at that, and I'm giving everybody about 10 minutes. So now I'll probably call everybody back to the main room at 9:35.
Okay.
Okay? How's everybody going on question 4?
I have like no idea what I'm doing, to be honest.
No idea? Okay, so let's have a look. I'll just oh, I might have to just share a screen, so let's share that one. Okay, so like I said, there's 3 ways to do it, but we can't use the equivalent resistance way. So the other 2 are the open circuit voltage, short circuit current technique, and the applier voltage technique. The only restriction on the open circuit voltage, short circuit current technique is to that you need to have at least one independent source, and we have one independent source. So the open circuit voltage, well, as I said earlier, we just get a voltmeter and we pretend we're measuring across the outputs there. There's no current flowing through here, so that the voltage VOC here is the same as the voltage at that node there. And this one, it's actually pretty straightforward, right? I should have turned that back on. Because this is a current source and there's no current flowing through here, we know that Ix for this first open circuit version is equal to 30 milliamps, right? Because we've got 30 milliamps flowing there and it doesn't go anywhere else. And that means it's pretty straightforward to figure out what VOC is, because we know the current flowing through it, we know the resistance, so we just apply Ohm's law. Okay? That's the first, it's the start of it. And then the other one, the short circuit current, you put an ammeter in here, which means you've got a short circuit across the current, across the terminals rather, and the aim is to figure out what ISC is. In this case, it's a bit harder because you've got to do a mesh analysis, right, with I1, and I'd call that I2 or ISC. It's the same thing, right? And you've got to apply a mesh analysis in order to solve that for ISC. Does that help at all?
Yeah, that helped a little bit. I gotta study more on this.
Okay. So anybody else here got any questions?
In both cases, as you said, we need to find VOC, either for the open circuit voltage and short circuit current.
Right, so there's sort of two circuits you've got to analyse. One of them is when there's nothing connected between A and B, and the other one is where you've got a short on A and B. But in both questions 3 and 4, because this technique is applicable, you do the same thing, right? It's one of them is the other one is a little harder, because it's got a voltage source instead of a current source, so you've got to do a bit more work in order to find VOC. But this question 4 is a little easier because of that current source.
Okay, got it. Thank you.
You're welcome. Okay, I'm going to move up to the next breakout room. Hi, how's everybody going with question 3?
Hello. Personally, I'm kind of struggling with it, but
Okay. So let's have a look. Let me just see if I can. Go with that. Okay, so the first part is to decide which technique you're going to use, and simply because you always need the VOC, the open circuit voltage, which is what that black tool is doing. We're up at that. I recommend at least trying the open circuit voltage short circuit current technique to start with. The only caveat or the only problem with that restriction on that technique is you need to have at least one independent supply, and you've got one independent supply here. And then because there's no current flowing through this resistor, that means this node here is also VOC.
Professor,
Yeah?
when you're writing in black on a screenshot or a file, when you're using dark mode, that shows up as white for us in OneNote.
Oh, does it? Oh,
Yeah.
that's no good. I wonder. Oh, I'm wondering. Ooh. I'm wondering if I select that. I'll avoid using it from now on. But if you could just let me know whether this comes up in black or white, that might be good to know. Okay, sorry about that. So let me not use that color then. Thank you for telling me that. I didn't know that.
Yeah, I'll post a screenshot of what it looks like on my end because I can't switch it to dark mode in the actual browser
Right.
version of OneNote.
Right. Okay. Thank you for that. Good to know. Yeah. So VOC is the same at the output as it is over this, and now what we've really got sort of is a well, we need it's basically a mesh, right? In this, I'm going to call it I1, but in this case, because there's no current flowing through this resistor, it's the same as IX. The reason I'm not labeling this as IX is because we also need to solve when there is current flowing through that 560 ohm resistor, and that's when the short circuit current here is here, which is either ISC or I2. I'll call it ISC because it's the same. Okay, so that's that is at least I think an attempt to start. I've gone way over my 10 minutes, so I might just quickly check in on the other groups, and then I'll call everybody back. Okay?
Okay, thanks.
You're welcome. So I've gone way over my 10 minutes so far. Does anybody have any questions about question 2?
No, I think it makes sense.
Okay, very good. I'm just going to check in on the top breakout room, and then I'll call everybody back. Hi, how's everybody going? I've gone way over my stated 10 minutes. I'll have to rethink my timings. But you okay, John? You?
I'm just still working through I guess how to tackle this. I've laid it out and I'm trying to work through it, but
Okay.
I at least am not done. I don't.
Okay. Well, we
No.
can keep going. I might do that. So give it another 5 minutes. So wait until about 9:45. Okay. We'll see how we go.
All right.
Sounds good. Okay. So everybody else is having problems too. So I'm going to give another 5 minutes. So we'll wait until 9:45, and I'll call everybody back then. Yeah, everybody else is having problems getting started this morning, so we'll wait until 9:45 to bring everybody back to the main room. Everybody else is having problems getting started, so I'll wait another 5 minutes or so before bringing everybody back to the main room. Okay?
Alright, thank you.
You're welcome. Okay. Um, so I'm going to put a poll in the discussion to see which question we should tackle first. And I'm not sure I'm doing this correctly. Let's try this. No, that didn't work. No, for some reason it's not doing it. Okay, let's just I'll ask somebody. How about that? So Giovanni, which question should we tackle first? Number one? That was easy. I should have just gone with one to start with. Okay. So let's have a look at the question. So we've got, so we want to solve it using superposition, and we want to solve for Ix. So independent supplies, we have two independent supplies, so we need to split the let's see if I can move that out of the way a little bit. There we go. So we need to split the problem into two. So I'll split the page into two. And the first one, we need to choose one of them, and I'm going to choose the IS. So does anybody want to tell me? Yeah, I've been going ahead and doing it. Does anybody want to walk me through how to do it? Giovanni, you brave enough? That's okay, I'll go with it. So IS is 600 microamps, right? And we have a resistor, and then all the way over here we have another resistor. And just so we don't forget, we have a ground there. And I probably shouldn't have drawn that 600 all the way over, because we have a resistor there. So this one is 2200 ohms, this one is 4700 ohms, this one is also 2700 ohms. And then our voltage source is the one that we're replacing with its ideal. So we just have that, right? And we're interested in this value of the current, and I'm going to call it IX1, right? Because this is option 1 and we'll do option 2 over here when we replace the current source with its ideal. Now that replacement does something a little strange, right? It places a short circuit over the 5600 ohm resistor. And that means that that resistor plays no role in the analysis. There's no current flowing through it because there's no voltage across it, because that short is there. Let's go with, right, because that short is there, this whole node, this whole region is a single node, right? Because I can basically walk along a wire to any of those parts of the circuit, and that means there's no voltage drop across any of that. So the voltage on one side of that 5600 ohm resistor is the same as the voltage across the other side. Okay, so then we need to do some work. So it's not that much work, but it's a bit of work. And I'm going to define my I1 to be going that way, and I'm going to define my I2 to be going that way. Now, you could solve this circuit using mesh analysis or nodal analysis, or you could try doing it just using series and parallel resistors and voltage and current dividers. That might be a little harder, but it's doable. In fact, you could probably do it using a current divider relatively straightforwardly. But I've decided my personal favorite is mesh analysis, and in particular for this question, it's relatively useful because for two reasons. One of them is we want to find Ix, and as soon as you have a question where you want to find a current, you should think about mesh analysis, right? Because mesh analysis gives you currents as answers. Nodal analysis gives you voltages. So that's the first reason I thought mesh analysis might be good. The other reason is because there is a current source. We already know what I1 is, right? I1 equals Is. It's the same. I1 flows through that current source. So we already know, without really thinking about it, that I1 equals Is equals 600 microamps. Okay? So that's the first piece. And the second piece is to do the mesh analysis, right? So for the mesh, the I2 mesh, we have and remember our polarities on either side of each resistor. So 2700 I2 plus, what's that, 4700 times, now it's going to be I2 plus I1, so I2 plus 600 by 10 to the minus 6, and that equals 0. Right, so we've got, what's that, that's 6700, 7400 I2 equals, and it's going to be minus 4700 times 600 by 10 to the minus 6. Okay, so I2 should equal minus 4700 by 600 by 10 to the minus 6 divided by 7400. And I forgot to start up MATLAB, so let me do that now. Where did it get to? There it is. I keep getting distracted by the orange color of the PowerPoint icon.
What was throwing me off with this one was I wasn't sure if I was supposed to put like a third loop on the last one.
Right, and like I said, that's it's certainly confusing, right? But as soon as we'll see in the next part, as soon as you can say there's no current flowing through one of the resistors or one of the circuit elements, you can effectively ignore it. Okay. So in this case, because that as I drew in the lilac color there, the light purple, because it's the same node on either side of that 5600 ohm resistor, it doesn't take part in the analysis. It's just a it's just for confusion in this particular example. We'll need to use it in the next one, but for this one, it's not. So let's just quickly okay, so let's see if that will work. So I2 equals, this is Q1, I2 equals minus 4700 times 600 times 10 to the minus 6 divided by 7400. Right, so let's just multiply that by 1000 maybe. So it's 0.38 minus 0.3811 milliamps. So that's let's just, oops, don't you hate that? I'm just going to take a screenshot of that, and I'm going to have to restart OneNote, because when it goes like that, all of the text just stays in place. Let's see if we can insert a picture. Oops. That's a bit bigger than the original, so let's just see if we can get it roughly the same size. That'll do. Right, so and what did I say? Minus 0.3811? Yeah. So I2.
Is that microamps or milliamps?
So where's it gone? There it is. Right, so I converted everything into amps, right? 600 by 10 to the minus 6. So this is in amps, and then I multiplied it by 1000 to get it into milliamps. The other way to say it would be 381.1 microamps. Right? So I'm okay with either. In fact, why don't we do that one? Why don't we just write it down as minus 381.1 microamps. And again, I'm okay with either milliamps or microamps because this question has the original current for IS in microamps. Let's just keep it in the same units so that it's a bit easier to compare. Okay, thank you. Yeah?
Sorry, I meant it as I got 3.81 microamps, not 381. Like I might have messed up. Let me find it.
Okay. All right. I'm not sure. I think I got it right. Let me just check that I typed it into MATLAB. Right, so minus 4700 times 600 by 10 to the minus 6 divided by 7400. I think that should be okay. And that by 10 to the minus 4 usually means it's in the hundreds of micro somethings, microamps in this case. Okay, so that's our first, and I didn't use it, but that's actually also equal to the first value of IX1. Okay? So now we've got to go back and do the second piece, and the second piece, remember, we want to replace IS. We keep VS and we want to replace IS with its ideal, and its ideal is nothing more than an open circuit. Right, so we've got a gap in the circuit there, and this time we're leaving in VS. So we've got 2200 ohms, we've got 4700, we've got 2700, we've got 10 volts, we've got 5600 ohms. Oops, 5600 ohms. Okay, and the thing we want to find again is IS, and again I'm looking at this part of the circuit because there's going to be no current flowing through that gap. This this resistor takes no part in the circuit. Right, it doesn't do anything. There's no current flowing through it, so there's no voltage drop across it. So then I'm going to have a look here, and my IX. Well, let's have a look at this IX. We might be able to do this pretty simply, right? I can redraw that. Now that I'm taking out the 2200, I can redraw that circuit diagram as Ryan is just asking whether the video is freezing. Is that, it could be my computer. I noticed my computer's being a little glitchy this morning.
Discord's just acting up. I've gotten kicked out like 2 or 3 times already.
Oh, really?
Like, yeah, Discord's just crashed on me like 2 or 3 times.
Yeah, I did hear they had an outage the other day, so I'm wondering whether it's the similar sort of thing. I'm wondering, the only other option might be to watch on YouTube. The only trouble with that is there's about a 20 to 30 second lag between when I say it and when it appears on YouTube, because I think there's a bit of a buffer on my local machine before it goes out to the YouTube stream. Okay, that's no good. I'll continue, and I don't have much control over the I've forgotten what the issue was with Discord. Anyway, So if we can redraw that diagram like this, right? And the thing we're interested in is IX, and this is going to be IX number 2. Excuse me, where this is now our 5600 ohm. Excuse me, I need to have a drink and cough. Now, oh, sorry about that. Oh, yeah, I think it's spring. Right, so there's the 2700 and there's the 4700 ohm. So now we can just redo that into a single equivalent resistor. Right. So this one we could say R equivalent is equal to 5600 in parallel with 7400, right? 2700 plus 4700. And let's just see what that is. There's MATLAB gone. So REQ is 5600. Oops, let's do it this way. 1 on 5600 plus 1 on 7400. Right, so it's 3.188 kilo ohms. Or 3188 ohms. And then I can just say that my IX2, well, let's just undo that last bit. IX2 is equal to what is it? V equals IR, so I equals V on R. Right, so it's 10 on that number. So Q1 I22 is equal to 10 on REQ, and I'm just going to multiply that by 10, or 1000 rather, to get it into milliamps. So that was, I didn't read it before 3.137. Right, so that's 3.137. milliamps. So then my total is going to be the addition of those two numbers, right? So Q1 I2, which is that one, Q1 I2 plus Q1 I22, and it's going to be 3.1. That's probably because, so it's just a little bit less than this one, because the first value is in microamps, and this one is 3,137 microamps. Sorry, no, I got that wrong. Let's try that again. I should have done that so that I get it in amps, right? And then the summation is more like that. So the Q1 answer is that, and then I can multiply that by 1,000 to get the right, so 2.756. So IX, let's just do it in green maybe. So IX equals IX1 plus IX2 equals 2.756, and now it's milliamps. Okay, so in this particular question, we didn't have to do too much out of the ordinary. Sometimes you'll have to do a full mesh analysis or a full nodal analysis. We sort of did one loop of mesh analysis in the first half of the circuit, and I could have done mesh analysis in the second half, but I noted that it was just a 10 volt voltage source going into some resistors in parallel, and we're interested in the total current, so it was going to be easier to just figure out the equivalent resistance and calculate the current using that equivalent resistance and the voltage value. Any questions about that one? Okay, so let me so Alex, which question should I do next? Alex Reeves? No? So what I might do is I might skip question 2. I'll do question 2, but I'll skip question 2 and go to question 3 next. And okay, so question 3. As I said, there's 3 ways of doing these questions. For this particular circuit, the first way, the equivalent resistance method, we can't use because of that dependent source, that 2400 IX. So in order to, because we always have to find the open circuit voltage, I normally just go with the open circuit voltage short circuit current technique. The other option is the apply a voltage technique, and I might use that. Using that approach in the second question, in question 4. But for this one, I'm going to use the open circuit voltage short circuit current technique. And to do that, so I get my, let me just overdraw this because I think it's probably come out in white on the web. So I just get my fictitious virtual voltmeter, and I stick it between the terminals A and B, one probe on terminal A, the other probe on terminal B, and that means I'm measuring the open circuit voltage. Because there's no current flowing, and just as an aside, when you have a voltage source, when you have a voltage meter, oftentimes a way to model it is with a very big resistance, because that voltage meter really does need a tiny little bit of current to work. All right, but for a voltage meter, you want it to be what's called really high impedance, because you don't want it to affect the circuit much at all. So something like 10 mega ohms or 100 mega ohms is what you would expect the input impedance of a voltmeter to be. Similarly, I'll talk about that in the next part of the circuit. Okay, so because we're measuring there, and because there's effectively no current flowing when we've just got the voltmeter connected, that means that this node is at the open circuit voltage 2, right? So there's no current flowing through here, so effectively that's a short, because there's no current flowing. So then we need to figure out the voltage there, and there's a couple of ways we could do this. I think the easiest way is to just use mesh analysis. The reason I say that is because nodal analysis, maybe we could do nodal, but we need to have a supernode there at the across that dependent source, right? So that could be, let's try nodal, right? Let's try nodal analysis, right? So there's A, there's B, and let's call this C, right? So there's the nodes, and at A we already know, right? So VA equals 16 volts, it's direct. And then we need to merge nodes B and C, right, into a supernode, because there's a voltage source there and we don't know the current flowing out of a voltage source until we've finished the analysis. So but one thing we can say is that so the KVL at the supernode, we can say that is equal to VB minus VC equals 2400 IX. Okay, and I think that works. And then the KCL at the supernode right, we've got that current and we've got that current, right, and that's pretty much it, because there's no current flowing in our open circuit voltage through analysis through the 560 ohm. So the KCL at the supernode is going to be VA minus VB on 3900, right, that's the current through the first resistor, and then minus VC on 4700. And that equals 0. Now we've got a slight problem in this one is because we've got IX, but we know that IX is just equal to VC on 4700. Okay, so really we can write this equation out as VB minus VC equals 2400 on 4700 VC, or we can move that across. So what's that? That's going to be VB minus 6700, 7100 on 4700 VC equals 0. And this one we can use our 16 volts, so we've got minus VB on 3900 minus VC on 4700 equals minus 16 on 3900. Right, just by substituting 16 volts into what VA is. Okay, so then we can plug that into an RF. Right, so this is Q3. And our matrix is 1 minus 7100 on 4700, 0. And then minus 1 on 3900, minus 1 on 4700, minus 16 on 3900. So this is Q3 ANDs. Okay, so we've got VB is 10.33 volts and VC is 6.836 volts. Let me just flick that away maybe, so I can use my second screen. Okay, so that means that VB VC equals 10.33 and 6.836, both to 4 significant figures. Okay, so we've got our VC, so our VC is our open circuit voltage, right? So our VOC is 6.836 volts. So that's the first one. And then now we've done the open circuit voltage piece. Now we need to do the short circuit current. And just like I was saying about the reason why a voltage source needs to have a high impedance is to have as little effect on the circuit as possible. All right, so that's a voltmeter. an ammeter, and let's just, an ammeter wants to have as little resistance as possible. So if we were in the lab, you would notice that the multimeters we use have a common black terminal, but then for measuring voltage they have one red terminal, and for measuring current they have a different red terminal. And the reason they have different terminals is because of the different input impedances. Let's see if I can probably want to go there and there and there. Do I have a picture? There we go. Let me see if I can pull it up. Sometimes I think my computer is dying, so sometimes it doesn't come up with files nicely. Right, so this is a picture of the multimeter we have in the lab. In fact, let me take a copy of that and put it over here so I can draw on it. Where'd it go? It didn't go anywhere. Let's save image, maybe? Probably didn't like that either. Let's just download it. So where were we? Up here. So I just want to insert that no, not a printout. I want to insert a picture from downloads. Okay, so for the multimeter, you always use this input here. So this is the common, the common or the ground, right? And then here you can see if you're measuring voltage or resistance or a diode or a capacitance, you use this input. And here you can see if you're measuring current, you use that input. And that's a difference between measuring current and measuring amps. Sorry, a bit of an aside, but I thought it might be worthwhile talking about. So we're measuring the short circuit current, right? And now we've got to do the way I drew it before. We've got to do, I think mesh analysis is the best way to do it because we're after ISC. And whereas before with the open circuit voltage, we were after the open circuit voltage. So now we want a current, so it's best to use mesh analysis. So let's have a look at the mesh. Right, I've already drawn I1. So let's we want the KVL for I1, and it's going to be minus 16 volts plus 3900 I1, and then it's plus 2400 IX, and we need to replace IX, and then it's plus 4700 I1 minus ISC. And that whole thing equals 0. Now let's just have a quick look at IX. IX is equal to I1, because I1's going in the same direction, minus ISC. Okay? So we can write that down as minus 16 plus 3900 I1 plus 2400 times I1 minus ISC, and then plus 4700 I1 minus ISC equals 0. Okay, and then for KVL for I2, what's up?
Professor, before we go to the second current, a couple of questions.
Okay, go for it.
What does ISC stand for? And also, can you repeat why I sub x equals I1 minus IC?
Okay, yeah, so what we're doing is we're applying the open circuit voltage, right, which we got down here, and short circuit current technique, right? So the OC, and let me just grab a highlighter, right? The OC is what I'm using for here, right? And then the short circuit is what I'm using for here, right? SC is short circuit. That might not have been the best highlighter to use for that color. Let's just maybe use maybe blue will be better, so you can read it a bit better, right? So that's what the SC and OC stands for. Short circuit for SC and open circuit for, I probably should have done that as well. Okay, and now you can't read it at all. Oh well, I'll leave it alone. I'll leave well enough alone there. So then the question about how do you get IX? Well, IX is the current flowing down here, right, as we drew, right? There's IX there. And because of the way I drew I1 going that direction, that's in the same direction as IX. And ISC is going in the opposite direction. It's going back up through the 4700 ohm resistor instead of down. So that means I1 minus ISC is the same as the current flowing through that resistor, so that's just IX. Does that help?
Yes, thank you very much.
You're welcome. Okay, so and I don't know whether I might just have to make a things a little smaller so I can fit everything on the page. I'll make it bigger again later once I've finished. So maybe the video isn't the best as it is. So now the KVL for ISC, we've only got, and I'm going to need to go down a little bit. There we go. So we've got 4700 times, now it's ISC, and this time we're interested in things with respect to the ISC direction. So now it's ISC minus I1, and then plus 560 I1, and that equals 0. Okay, so there are our two equations. Now I might need to reorder. I've got to group, distribute and group like terms. So let's just do that for this one. We've got 3900 plus 2400 plus 4700, right? So 3900 plus 2400 plus 4700 times I1, and then we've got, I'm going to go minus, and it should be SC there, 2400 plus 4700 ISC, and that equals 16. Okay, and then the red one, it's a little easier. It's got, looks like it's oh, I got that wrong. The current flowing through 560 is ISC, not I1. So that should be ISC, not I1. So then it's what's that? 5260, is that right? Yeah, it looks right. ISC minus 4700 I1, that equals 0. So now we have our two equations in two unknowns, so I can bring MATLAB back maybe. And then we can do our, this is, which question is this? This is question 3, and it's RF2. And we've got, I'll do I1 first, so minus 4700, 5260, 0. And then if I do I1 first, that's going to be 3900 plus 2400 plus 4700. Oops, I wanted a plus, not an underscore. So that's that, and then minus 2400 plus 4700, and then 16. That looks about right. And then we can do a Q3 ANS 2 is RF Q3 RF 2. And so we get that. I'm just going to see if I can multiply it by 1000 to get, or maybe format long. There we go. So we've got I1 is 3.436 and ISC is 3.071, both in milliamps. So let's just write that down. If I've got space, I might just do it over here. So let's just take that up here. So that means that I1 and ISC are equal to 3.436 and 3.071, and both of those are in milliamps. Okay, so now I have my ISC and I have my VOC. So now I can get the answer that I'm really after, right? So that means that my RTH is equal to 6.836 divided by 3.071 by 10 to the minus 3. And that equals, I have no idea. Let's figure out what it equals. Right, so it was VTH, so Q3 VTH, RTH. This is the Thevenin resistance, 6.836 divided by 3.071 by 10 to the minus 3. Right, so it's 2.226 kilo ohms, or 2,226. So now we have all the information. One thing I'd like you to do when you have these questions is to write down the answer. Where have I got some room? I might have to go all the way over here. Right, write down the answer like this. Right, so the Thevenin equivalent is like this, right? And we know that the voltage is 6.836 volts, and that's VTH. And we know that RTH is equal to 2226 ohms. And our current source, our Norton equivalent circuit, is like this. Okay, and our current was 3.071 milliamps, and our Norton resistance is the same as our Thevenin resistance, 2,226 ohms. Okay, I just like having the answers displayed like that, just so it's clear. You understand what you've been doing, and it's just an easy way to show the answer. It takes a bit more space, but I think it sums up the result nicely to draw it like that. Okay, any questions about that? And we're way past time for a break, so I'm going to take a break very soon. But I'll take any questions now, or we can wait until after the break. Okay, if there are no questions, I'm going to take a slightly longer break. Let's make it a 15-minute break. And then when we come back, I'll do questions 2 and 4 on the tutorial sheet. Okay, so let's try a 15-minute break. 15-minute timer, there we go. And we'll go with that. Thank you very much. Okay, so we're maybe back. So I had a question via
Professor,
direct.
you're muted.
Oh, I'm still muted. Thank you. Thank you for telling me that. I should have known. Anyway, I had a question via direct message. So just a general suggestion, please, if you've got questions about stuff that's happening during the lecture, use the discussion-236 text channel. It's just easier for me to, I have on my other screen, I have my video mixer and I have Discord running there, and I don't want to have to keep chopping and changing the channels on Discord. So I keep an eye on the, I don't necessarily always notice it, but I keep an eye on the discussion 236 channel for text messages in case somebody doesn't have audio, and I'd rather not have to click out of the discussion 236 channel and go to DMs to find questions. So I had a question that the short circuit current should have been something more like 1.73, and I'm just going to go have a look at what's happening here. So for a start, I would have thought it 1.73 amps seems a little high, right? So maybe 1.73 milliamps is going to be, well, yeah, 1.73. I'm not quite sure how to get there. Stephen, do you want to talk me through how you got there and where your numbers? Are you saying that there's an issue with the calculation, or did you have a different approach to getting the answer? Oh, okay. So you used something like this equation here, and just did a substitution of this back up into the first KVL. Yeah. So let's that might be easier than doing the MATLAB approach, right, or the RF approach. So let's see about doing it that way. So I'm going to get I1 on one side because we're interested in ISC, so it'd be nice to get ISC directly, right? So I might just draw on the top of the multimeter. Hopefully it won't get too confusing, right? So that means we've got I1 equals, now what's it going to be? It's going to be 5260 on 4700 ISC. Right? Can you see that? So we move 4700 I1 over to this side, so it becomes positive. and then divide both sides by 4700, so we get I1 equals that. And then we can substitute that into here, right? So we get 3900 plus 2400 plus 4700 times 5260 on 4700 ISC minus, what was that again? 7,100 ISC equals 16, right? And then we'll take that up here, and that means we get what is it? ISC equals 16 divided by, now what's it going to be? It's going to be 3900, and I'm going to need a bracket, so 3900 plus 2400 plus 4700 times 5260 on 4700, and then minus 7100. I think that's right. Let's see what that comes out to in MATLAB. No, I'm going to grab there. And I might need to make it a bit smaller. Right, so ISC equals 16 divided by, and I think I'm going to need two of those, 3900 plus 2400 plus, not underscore, plus 4700 times 5260 on 4700 minus 7100, and that gets us 3.071 milliamps, which I think is what we got before. Yeah, 3.071 milliamps is the same as the answer we got before. Okay, is that okay, Stephen? Okay, very good. So, but it's good to see that, right? Once you've got an equation like this one here, let's go with highlight. Once you've got an equation like this one, right? And there's only two equations with two unknowns. Maybe that's an easier way to solve the problem, right? To do it using substitution rather than the RF or the matrix valued approach. Okay. So that was question 3. I'm gonna go back and do question 2, the superposition question. Okay. So we're aiming to find IX, and we've got two independent sources, so we need two separate circuits. So again, I'm going to break our diagram in half, and the first one I'm going to keep the current source. Okay, and when I replace the voltage source with its ideal, again I just get a wire, and I'm just going to ignore R4, right, because it's completely shorted out, and I need to know what IX is. And this one is, let's just write all the values. This one's 400 microamps, 400 microamps. This one's 220 ohms. This one's 4700 ohms. And this one is 3900 ohms. Now, this one, I'm not sure what the best way to do this one is, because it's current. So my first thought would be mesh analysis or current dividers, right? Because I've effectively got a current here of 400 microamps, and it's going to be split somehow between the 4700 ohm resistor and the 3900 ohm resistor. So I could just do the use a current divider. The only slight wrinkle in using a current divider approach is that the way I've drawn my purple current going through 3900 ohm resistor is that it's going in the opposite direction of IX. So the value I get for IX is going to have to be negated. Or rather, the value I get for the purple current through the 3900 ohm resistor is going to have to be negated. But I'm going to do it that way, right? So IR3, and all we need to know is that IX equals minus IR3. Okay? So that sort of works. So now what? How do we get IR3? Well, IR3 is equal to, and it's a current divider, so we need the resistance in the other branch, so it's 4700, divided by 4700 plus 3900, okay, times IS. And we can type that into MATLAB maybe. Right, so 4700, this is IR3, is 4700 divided by 4700 plus 3900. Keep doing that today. And then we have 400 microamps. I'm just going to leave it at 400. So that's 218.6 microamps. Okay, that's IR3, but remember this is, and this is, I should have said IX1. So IX1 is minus 218.6 microamps. So then we do the other way, and again, if I replace this current source with its ideal, which is an open circuit, R1 doesn't take any part in the analysis. So I'm just going to draw from R2 onwards. Right, so there's our 4700 ohm resistor, there's our 3900 ohm resistor, there's our IX, there's our 4700 ohm, and that's our 12 volts. And just like in the other one, I could do this using equivalent resistance, and so I think I'm going to do the same thing. So we can redraw that diagram as effectively that, right, where this is 3900, this is 4700, and then we have 4700 here. Okay, so my R equivalent and again that's 12 volts. My R equivalent is 4700 in parallel with 3900 plus 4700. So I can do my R equivalent there. So that's going to be 1 on 4700 plus 1 on 3900 plus 4700. Right, so it's 3039, 3039 ohms. So that means my IX2, and this is, I should have put a 2 there, my IX2 is equal to V on R, 12 on 3039, and that equals, swapping back to MATLAB, 12 on REQ2 is 3.949 milliamps. Okay, so then the overall answer, IX total, is equal to IX1 plus IX2, and that I should use brackets or parentheses around those to make sure it's not taken as squared. Right, so it's just the number 2, and so that's going to be minus 218.6 by 10 to the minus 6 plus 3.949 by 10 to the minus 3, so it's going to be about 3.7-ish milliamps. So did I got that IR3, so let's just call this IR32. So Q2 ANDs equals IR3 plus IR32. Oh, I didn't put that one into microamps, so I need to let's try that again. IR3 is that. Oh, that's because I forgot to negate it. There we go, that's more like it. 3.730. Okay. So that's the second superposition question. And any questions about the superposition questions, either this one or the other one? So one of the things I want you to be able to do is figure out the right technique to use. When I ask about superposition, I usually don't tell you anything else, right? So you could use mesh analysis, you could use nodal analysis, you could use current dividers, you could use voltage dividers. It's up to you. Sometimes it doesn't make a lot of difference complexity wise. So sometimes it's just as easy to use one as or the other, so you can use whatever you're most comfortable with. Depending, I think the current, I haven't been keeping tabs, but the current ratio is, at least for this mesh analysis versus nodal analysis, is about 2/3 of the students prefer mesh analysis and about 1/3 of the students prefer nodal analysis. I'm okay with that. It's just that if I ask you to solve using mesh analysis, you need to solve using mesh analysis. If I ask you to solve using nodal, you need to use nodal. In the final, not in the next oral, but in the final, not in the next midterm rather, I probably won't ask you to solve one way or the other. It's going to be up to you to figure out a solution, and I really don't care how you solve the problem. In the run-up, in the two midterms, I do care how you solve the problem, because I'm trying to get you to understand the techniques. And so I need to see that you understand mesh analysis and nodal analysis and superposition and Thevenin and Norton. But in the final, I'm mainly after the answers, and how you get there is up to you. Okay. So, question 4. Right. Again, Thevenin and Norton. And we already partially did this, right? So because there's a current source on the left-hand side of 30 milliamps, and if we think about this circuit using mesh analysis, and again, the reason I'm doing that is because it's currents, and currents tend to work best with mesh analysis, or current dividers, but mesh analysis too. And if we've got 3 options for solving for the Thevenin resistance. The first option is off the table, equivalent resistance. That doesn't work because we've got a dependent source, so we can't do that way. So we need to use one of either open circuit voltage, short circuit current, or apply a voltage. I thought maybe we should try the apply a voltage technique for this one to find the Thevenin resistance. Okay, because we did the open circuit voltage, short circuit current technique before. We still need to actually find the open circuit voltage because we won't get that out of the apply a voltage technique. But let's try the. I apologise for my dog going ballistic in the background. Sounds like yeah. Oh, she doesn't like dogs, but she likes cats, and that sounds like the neighbour's cat just walked across the front yard. And the yowling means she wants to go out and say hello. Okay, sorry about that. So yeah, let's try the apply a voltage technique, right? So apply a voltage technique does the following. We take the circuit. In fact, let's just have a look at the what was it? Thevenin and Norton. Topic 8. Right, so the apply a voltage technique. Right, and let's just, I'm gonna take a screenshot of that and move it over into our tutorial 3. So we can do that, and we will come, oops, I didn't want to go there, I want to go down here. Right, and we'll insert that screenshot picture. And not downloads, I want it to go into screenshots. Right, so apply voltage. So we've got the instructions right here. Right, so we remove the load. If the load's already removed, there's nothing between A and B. Replace all independent supplies with their ideal resistances. Right, so in this case we only have one independent supply, the current source on the left, the 30 milliamps. So we replace it with its ideal, and its ideal is just an open circuit. Okay, so if we do that, we effectively have a circuit like this. And then we place a voltage supply between the nodes where the load will be and give it a name, so, or a number, right? So we'll place our voltage source and our V new. I'm just going to say 10 volts, right? 12 volts does, 1 volt does, anything. And let's just write down the numbers: 2700 ohms, 680 ohms, 8100 ohms, and this is 1000 IX, and IX is here. Okay, so the funny thing about this is that because there's no current flowing through here, we can just ignore that part of the circuit. So now what we want to try and find is I new, right? And I new equals V new on, well, that's just a 680 ohm resistor in series with an 8100, so it's just 680 plus 8100. Okay, so that's 10 on 680 plus 8100. That should be 680, not 68. Oh, drat. Sorry, I'm going to have to quit OneNote again and restart it. I should have taken a screenshot. Oh well. So again, as I said earlier, we can basically ignore that part of the circuit and that part of the circuit. And what have we got? We've got an 8100. Maybe make it a bit thinner. And we've got a 680 ohms. And I said my VNU is 10 volts. So what we're interested in is INU. So INU is 10 on 680 plus 8100, which is whatever it is. Right, so 10 on 680 plus 8100. That's that 1.139 milliamps. Okay, and in fact I can already see, right, what the RTH is. It's really just 680 plus 8100. So there's my RTH. Now remember, in order to write down the Thevenin and Norton equivalents, I need to be able to write it down RTH, which we have, and VTH, which we haven't got yet. And then for the Norton equivalent, we need Rn, which, as we know, that's the same as the Thevenin equivalent, right? So Rn is also equal to 8780 ohms, but we need to know what In is. So I need to, there's a relationship between all of that, right? So VTH equals In RTH, which equals In Rn, right? So the Thevenin and Norton equivalents follow Ohm's law, but we need to find, we've only got one of those numbers. We've only got RTH or Rn. We don't have either the current In, the Norton current, or the Thevenin voltage. In order to get the Thevenin voltage, we need to do the open circuit voltage test. So the open circuit voltage test, as I said earlier, we just take our voltmeter and we place it across where the load would be. And then because there's no current flowing through that 680 ohm resistor, the open circuit voltage here is the same as the voltage at that node there. And this one's pretty nice because we know what the current is flowing, right? So our open circuit voltage is just the current times the resistance. And let's see what that is. So it's 30 by 10 to the minus 3 times 8100, right, which is 243. That's a pretty big voltage. Okay, so the open circuit voltage is 243 volts. And that is my Thevenin voltage. And now I can use this equation to figure out what my Norton current is. So 243 divided by 8780 gives me 27.68 milliamps. I think that's right. Just check again. 27.68. Okay. So that's the tutorial 3, right? What I might do is I might put together some more example questions. In fact, I might have older exam papers that might help with getting some more examples of this. I also highly recommend going into Professor Broderick's book. Right, because there's let's see what page it's on. And we have equivalent circuits is what we're interested, page 111. So let's see if we can get to page 111. Not quite there yet. There we go, equivalent circuits. Okay, so this again, this you can see where I got the my screenshots from, and it goes through several other examples to figure out the Thevenin equivalent circuit in various techniques. So I suggest you have a look through that. Oops. Still don't know why it does that. Sometimes it just decides to flick immediately to the top of the page. Good examples there as well to have a look through. Okay, so far we've talked about Thevenin and Norton. We've done tutorial 3. I haven't spoken much more about maximum power transfer. There's not much more to say except the following. If I have a circuit right, and that circuit is going into a load, right, and if I want to know the load at which I get maximum power transfer, right, what I can do is I can replace this circuit with its Thevenin equivalent. And the maximum power transfer theorem says that I transfer maximum power when the load impedance matches the impedance of the rest of the circuit. So now, right, it's easy to see that RL at maximum power equals RTH. Because the maximum power transfer theorem says that the impedances have to match, right? If I can convert my circuit into a Thevenin equivalent circuit, then I know what the impedance match has to be. Now that was I'm not going to go through the derivation of the maximum power again. I went through that once. If you want to have a look at the video again, it's there. Okay, any questions about the tutorial?
Could you repeat how we got RTH on the last question, if you don't mind?
Yeah, okay. On question 4 in the tutorial. Okay, we can do that. So for this particular question, it's a little simplistic because because that current source has been replaced by its Thevenin, its ideal equivalent, right, which is an open circuit. It makes the circuit we analyze very simple. And in particular for the apply a voltage technique, it means that I can almost read off directly, because of the way the circuit is, I can almost read off directly that the Thevenin equivalent resistance is just the sum of the 680 ohm and the 8100 ohm, right? But I went through this apply a voltage technique. I took my VNU, I applied it, I noted that these branches are not in use, there's no current flowing through them, so we don't have to analyze what's happening there. And then I probably should have not taken the shortcut of just writing it down. So I apologize for that. But remember, this is just VNU on INU, right? The 8780 ohms. Okay, does that help?
Yes, thank you.
You're welcome. But it was straightforward. I didn't, but I should have written it out in full so you can see the steps. Okay. So let me just check what's happening in the assignment that I moved, or at least I think I moved. So we want homeworks 6 and 7 and lab 7. So homework 6 and 7. Let's just check that it's, I should have moved the due date for that to, ooh, it's a little slow, to the 10th. Haven't quite finished filling it in. So there it is there. I will display that until the 10th instead of the 3rd. That's homework 6. Now let's go to homework 7. And check that it's also not due until April 10th. Wow, April. That's a little scary. Don't know about you, but I find it scary. Not sure whether it's the internet or my computer or what. It's just a little sluggish right now. And that's already changed, so it's good. So, and the other one was, I think, Lab 7. So let me just make sure that that's up to date too.
Steven just dropped a message that apparently the YouTube stream is not working right now.
Oh, really? That's no good. It's not pretty. Yeah, that's not good. I wonder if I need to restart it. Okay, does that help? Okay, it's a little
Yes, thank you.
delayed, but it does seem to be going. Anyway, where was I? Homework, sorry, Lab 7, and I just need to make sure that that happens. Okay, so, yeah, definitely seems that the internet is not happy right now. I wonder if it's because of that big ship in the Suez Canal. That's, I don't know, I'm not surprised by anything after the last year. Okay, so I'm happy to take any questions about homework 6. Let's have a look at homework 6. I hope Professor Broderick's server is still up and running. Looks like it's running a little faster than Blackboard. No, maybe not. Okay, so let's just check. Homework 6 is, I think, the... Oh, I got them round the wrong way. Which one's due? I don't... Sorry, I'm getting confused. Yeah, homework 6 isn't due for a while, but let's have a look at it anyway. Homework 6 is Thevenin and Norton. So let's just go there. And let's have a look at the Thevenin and Norton questions. Right, so here's the circuit. And it basically just asks you to so this one's a bit different. Here the load is R3, right? So the aim is the circuit is a little different, but the idea is still the same, right? That you disconnect the load and you analyze the circuit with the load disconnected. And in this particular example, my Thevenin voltage is minus 53.78 and my Thevenin resistance is 5.556, and then because that Thevenin resistance is that, the maximized power dissipated is that, and then because I know the voltage 53, I can figure out what the power dissipated is by the load. Okay, let's have a look at the next one. So this one, there is a dependent source, so we can't use the equivalent resistance technique. There's our load. So the open circuit voltage is just going to be given by this voltage divider, right? R1, R2. Because well, it's not quite true. The open circuit voltage would be the voltage measured here when we remove the load. But we've got two things. This is a voltage source itself. It's a dependent source. Let's see what it's dependent on. It's dependent on Vx. So we can calculate the voltage here as just using a voltage divider, right? But then the voltage, the open circuit voltage, is going to be that voltage dropped by 0.5 Vx. So we need to do that calculation. And then the next part is we put back the load, and it asks for what the output voltage is when we put the load there. Oops, where was I? Web work, there we go. Okay, so let's have a look at problem 3. So problem 3 looks like it's just asking for the Thevenin equivalent, right? So how do we do this one? Well, we've got this is an interesting one, right? This one has no independent sources, so we cannot use the open circuit voltage short circuit current technique. We have to use the apply a voltage technique. Okay, so we apply a voltage to the nodes A and B, and then we analyze the circuit to find the I nu, the current coming out of that supply, and that will tell us RTH. Once we've got RTH, then we also need to figure out what the Thevenin voltage is, and we need to apply the look at the open circuit. We need to look at the open circuit voltage in order to do that, which open circuit voltage will be VTH. Okay? And then problem 4. Find the equivalent circuit for the schematic between nodes A and B using Norton's theorem. Enter the values for the circuit below. So now we're doing a Norton equivalent circuit version. So we want to find the Norton current and the Norton resistance, but remember the Norton resistance is the same as the Thevenin resistance. And in this case it looks like we have no dependent sources. So we could, for this question, use the equivalent resistance technique to find RTH or RN, right? And the equivalent resistance technique, the first step is to replace all the independent sources, we have 2, with their ideal resistances. So VS will be replaced with a short circuit, and IS will be replaced with an open circuit. And then we just have 4 resistors in a network that we should be able to calculate the overall equivalent resistance. R1 in parallel with R2, and then R1 in parallel with R2 is in series with R3, and then that whole resistance is going to be in parallel with R4. Okay, so that should let us figure out what the Thevenin or Norton resistance is. And then once we've got that, we need to, well, we want the current, so we need to find the short circuit current. So the short circuit current we'll need to put a short across A and B and then analyze the circuit that way. Putting a short across A and B means that R4 doesn't enter into the circuit. It's got a short across it. It's got the same voltage on either side of it, so it has no current flowing through it. So we just analyze that circuit to find ISC. Because it's ISC, it's a current, I'd probably recommend using mesh analysis to find that current. And that should allow you to find that one. And then problem 5. Ooh, this one's, what have we got? We've got the load over there on the right hand side. And we want to find the Norton equivalent again. So this one's not as easy because we've got a dependent source in V1. So we need to use either the open circuit voltage short circuit current technique or the apply a voltage technique in order to solve this one. And finally, again, another Norton question. And here we've got okay, source conversions. I haven't talked about source conversions. I should talk about source conversions. So you can solve this question without explicitly using source conversions, right? It's got 2 independent sources. It's got VS, which is an independent voltage source, and it's got IS, which is an independent current source. So you could just use the equivalent resistance technique in order to find the Norton resistance. Source conversions. Let's just have a quick yeah, sorry about that, Ryan. I hope the YouTube is okay. If it's not, I'll see about redoing at least part of the video for this and making that available. Okay, what was I saying? Yeah, source conversions. Just quickly, right, source conversions. And this is nothing more than noting that if you have a configuration like this, you can convert it to a configuration like this. Okay, that's all the source conversion is. It's just noting that the Thevenin equivalent and the Norton equivalent are equivalent. And you can swap one for the other, provided you get the right values. You get the right current, you get the right voltage, you get the right resistance. Okay, so here, for example, we could replace R1 and Vs with a current source and a parallel R1. Right, and then we'd have R1 in parallel with R2 in parallel with R3 plus R4, right? R3 and R4 are effectively in series. Okay, that's all the source conversion idea is, that you can replace a series voltage source, a voltage source and a series resistance with a current source and a parallel resistance. Okay, and I think that's all in homework 6. Right, I've put off, and what's the one due today? I've forgotten. So the only thing due today is the lab 6 is the superposition. Somebody had a question about the lab. So let me just have a look at the lab. Right, so
sorry, I do have a quick comment about the homework.
Okay, yep, go for it.
So, superposition is due next Saturday, correct?
No, it was, but I just...
Okay. It just hasn't updated on web work yet. Okay.
Oh, it has. Okay, yes. Sorry.
No worries.
Let me... why don't I do that while we're here, right? So let's make sure that web work is in sync with Blackboard. So Nodal, I set you then. So superposition and Thevenin. Superposition and Thevenin are due on the 10th. So let's just edit those. So rather than the 3rd, they should both be due on the 10th. Okay. So now Superposition and Thevenin are both due on the 10th. Okay, does that fix it? So Jacob just asked about rescheduling. I try not to put any effort into scheduling midterms. I have set up the Microsoft bookings link that you have, and I've set it up so that you can reschedule your midterms whenever you like, provided there are free spaces. Okay, so I want to invest 0 time in scheduling your midterms, and if there is a free space and you need to reschedule for whatever reason, just do it. No need to ask me. It goes straight into my calendar. The only reason you may need to ask me is if you need to reschedule and there are no free slots. In that case, we can figure something out. But that's perfectly okay, Jacob. No problem with that at all. Yeah. I try and work with the technology, and in this case, I was commenting to some friends the other day that I had the first shot of the COVID vaccine on Thursday, and some of my friends asked me whether I'd started converting over to loving Microsoft because of the whole meme about Bill Gates and 5G taking you over if you get the vaccine. So I actually said the Microsoft bookings, the thing that lets me give you a link to book your midterm, and in fact OneNote, modulo a few issues we have with the colors and the fact that it stops saving the what I draw in the right place sometimes. I actually find both of those better than other equivalents. So they were saying that I'm converting over to Microsoft. I just find OneNote at least as easy to use as Evernote, but the thing I really like about OneNote compared with Evernote is that OneNote lets me set up classrooms so that I can give you access to everything very easily. It's the single central Connecticut State University's single sign-on stuff, but that makes life easier for me to share my notes. And then the other equivalent to the bookings is a thing called Calendly, and the trouble with Calendly is I don't get the full use of Calendly unless I pay them, whereas because Central has a Microsoft subscription, I get the bookings piece for free. So yeah, so just yes, like I said, I want to invest as little time as possible in managing your time slots. It goes straight into my calendar, so I know when we're going to have your midterm, but that's perfectly okay. Okay. I had a brief run through homework 6. Does anybody have any did anybody have any lab 6 questions specifically? That's where I was going next, wasn't it? Okay, so the aim of this is to see how superposition works, and it gets a little squirrely. Let me which one is this? This is lab 6. Let's just download that. I'm just going to download it into my downloads folder. Did I do a lab 6 notes? I sort of did. Let's just do another one. Okay. So the first one is to just redraw the circuit with the each of the independent supplies replaced in turn. Okay, so the one thing to note about R3 in the voltage supply only is that there's no current flowing through it, so there's no voltage drop across it. And in the other part, the for R3, we know directly, I think it was supposed to be 5 milliamps. 5 milliamps, there we go. And it's gone gaga again. Let me just try drawing. So we know in this part that we have 5 milliamps. It's lost it again. Like I said, I do have some standards. Okay, so in the second part, let's go back to blue and thinner. And that should mean, what's our R3? Our R3 is 560, so that's going to be 5 milliamps times 560 to give us the volts of R3, right? And now, what this one is asking is, it's just asking something that is to write the total VR1 in terms of the numbers in these two tables, but in terms of the general expression. So that's just VR1 1 plus VR1 2. And similarly for all the others. This is superposition. We do the 1 replacing the first supply, and then we do the other replacing the second supply. And the sum, the algebraic sum, is what gives us the answer for all of the quantities, the voltages and the currents. And then question 5 is just asking you to add the entries in these tables to get values. Anybody got an answer for question 6? Let me see if I can bingo somebody. I've already spoken to Jacob. Let's try someone else. Sorry, Jacob. Joel, any thoughts about an answer to question 6? What is indicated if one of the algebraic sums in the previous step is negative?
My screen is loading right now because it crashed a second ago.
That's okay. So the question is, what is indicated if one of the algebraic sums in the previous step is negative, right? So we've got a V1 or VR1, and the value we get is negative. Is that any idea what that might mean? Okay, I'll try someone else.
I have like an incorrect loop. I don't know. That might not be the answer though.
Well, it's not so much incorrect, right? It just means that your guess at the polarity of either the voltage or the current was wrong, right? Whenever we put polarities on a circuit, either the direction of current flow or the plus and minuses to indicate the plus side of the resistor or the minus side of a resistor, we could get it wrong. We could actually have the voltage being the other way round. And that's all that's happening when the algebraic sum comes out negative. It just means that the direction or the polarity that we assumed on either the voltage of the or the current was going the other way. That's all what's happening there. And then the aim is to write down the KVL equations for each loop. Let's have a look at the loops. Right, so there's 3 loops. There's one loop. And let's go that way for that one. There's another loop. And there's another loop. Remember, these are loops, whereas the blue and the green ones on my screen now are not are meshes, but the red one is not a mesh because it jumps over the R2 branch, right? But it's still a loop. All 3 of those are loops. Okay, use your calculated values for the original circuit to write a KCL expression for node A as indicated. So there's node A, and the aim is to just say what the currents flowing into node A are, and to make sure they're 0. And then the aim is to do the same thing again, but now using LT Spice, and just make sure that you try and get your devices with the right current flow by using the control R to rotate the device so that the direction of current flow on your circuit diagram matches what LT Spice is doing. Okay, so you do the first version, you do the second version, and then you just sum each box from the previous 2 tables into this one, and then you construct the full circuit in LT Spice and do the same measurements. And the idea is that this table, and, well, it's not a table, but these numbers should all be the same. Okay, so there should be There might be minor differences in terms of just significant figures, right? There might be minor differences, so that's okay, but they should roughly all be the same. The voltages and the currents you get from the three approaches should all be the same. Okay, any questions about that one? No? Okay. Let's just go back to there. So it's a way off yet, but let's have a look at lab 7. That was lab 6, so let's, don't think I have a lab 6 tab, so let's add a lab 7 tab. And let's just see, like I said, I think my computer is slowly dying. Oh, that's right, I moved all of those out. So lab 7. See if that works. Maybe, maybe not. Okay, so let's see if we can insert that lab 7 in here. Okay, so this is a lab about Thevenin, Norton and maximum power. Right, and we've just gone through Thevenin and Norton. So I'm not going to talk much more about those. It's a bit of a pity we don't have an actual lab, because one of the things that is we need to use in this, if we're doing this lab in reality, is a thing called a potentiometer, right? And that looks like one of these things, and the electrical circuit of the potentiometer is either on the left or on the right. And basically it's a resistor with 3 taps, and the resistance R12 is whatever the value of the potentiometer is. Say it's 1K, so R12 is equal to 1K minus R23, right? So you get as you turn that knob, then you get an increase or a decrease in resistance values. And then the overall resistance, if it's a 1K, it'll always be 1K, the resistance between nodes 1 and 3. Right, so the first example is just to figure out what the voltage across R3 is. And I think the easiest way to do this one would just be as a voltage divider. So we have R2 in parallel with R3, and then that's in series with R1. So we can figure out the voltage across R3, which is the same as the voltage across R2, is equal to R2 in parallel with R3 divided by R2 in parallel with R3 plus R1 times Vs. Let me just write that out. Right, so VR3 is R2 in parallel with R3 divided by R2 in parallel with R3 plus R1 times Vs. And then the aim is to validate that by doing the same thing again in LT Spice. And then we're going to use R3 as the load resistance. So we want to draw how we get the open circuit voltage. So in both cases we take away the load resistance, so we remove R3. So for the open circuit voltage, we've just got that circuit, and for the short circuit current, right, we do have a resistor there, but because this current is just short circuited, this resistor doesn't take any part in the analysis. So we can get VOC, we can get ISC, and then both of these are just calculated from VOC on ISC. So then it just asks you to use LT Spice to measure the current and the voltages, the open circuit voltage and the short circuit current. Sorry, why is it when you flip the voltage source, the current and voltage of a resistor changes? Sorry, Stephen, I only just saw your question now. Well, can you explain that a little bit more? Okay, I'll come back and answer Stephen once he's given me a bit more to go on. So then we just do the same thing, but this time in LT Spice. And then it just wants you to redraw okay, So if you change the polarity to match the original question, the voltage and current values for R1 was higher than the calculated ones. That shouldn't be the case. I'd have to see the actual circuit. Would you be able to drop the .asc file from LT Spice into the chat, or DM it to me directly if the chat won't let you drop it in there? I think it should let you. That way I can have a look at it and bring it up in LT Spice on my machine and have a look at it. Okay? So, yeah, so the aim here is to just redraw the Thevenin equivalent, which is the voltage version, but this time put R3 back in place. And figure out what the current and voltage is, and then do the same thing again, but this time doing it in LT Spice rather than calculating it, and then redraw the circuit using the Norton equivalent and put R3 back in place. Right, so there's our R3, there's our IN, and there's our Rn, and calculate what VR3 and IR3 are now. I'll give you a hint, they should be the same as the one in the previous section, and then build the circuit for the Norton equivalent circuit. Oh, there's a video. I'd forgotten about the video. Let's see if I can pull that up. Did that come up before? I thought I pulled it up in Adobe. Is that right? Yeah, there we go. So let's see what the video, see if the video link still works.
Alright, in this video I'm going to show you how to simulate a maximum power transfer circuit.
Okay, so this isn't one of my videos, but it's I was going to do the same thing, and I felt I might just as well make use of DM Explains' video. So have a look at that one. And what it's going to do is it's going to make use of the function in LT Spice that lets you change a particular value over a range of values. So instead of just having a single operating point, you can change different. You can change LT Spice to vary at least one of the pieces over a range of values and plot that, and then it'll let you plot things with that. So have a look at that video. And yeah, basically what we're going to do is in LT Spice, we're going to vary RL from 0 to 10K, and we're going to look at the power dissipated by that variation in RL and figure out where the peak of that power dissipation is. Now, don't do this. If we're doing this in a lab, you can do all of the calculations here, and doing the maximum power lab physically is a little tedious, because first of all, you have to make sure you know what RL is. That, right, setting a particular value for the resistance is hard using one of those potentiometers. So you have to measure what the real RL is. It might be, you can set it close to 100, but it won't be exactly 100. It'll be 90 or 110 or 120. So you have to measure it, and then you need to measure the voltage and the current across it. So it's a little tedious, particularly for doing this number of measurements. But in LT Spice, it's pretty straightforward. And like I said, have a look at that video to do that. And then I probably should modify this. You should be able to do the plot that I'm asking you to do in Excel in the lab sheet. You should be able to do that. You should be able to do that plot in LT Spice. And I might see about doing a special video just for this lab, so you can see what I mean. Okay. I don't have anything else to talk about today, unless somebody has any other questions. I think I've done everything on my list of to-dos. I didn't talk much about maximum power, but there wasn't much to say about it. Does anybody have anything else you want me to talk about? Stephen, did you... Yeah, I don't have that... Stephen, if you can just email me the .asc file that you're seeing, I'll see if I can figure out what you're saying there about the polarity changing and the voltages changing. Any other questions? If not, let's leave it there for this weekend. No class next weekend. Have lots of chocolate. Celebrate Easter if you celebrate. Celebrate Passover if you celebrate. Have a nice break regardless. Okay, and I will see you in 2 weeks' time, or during your midterms if you haven't done that yet. Okay, thanks for your time.
All right, thank you, Professor.
Yep, bye-bye.